Okay, so in this video, we're going to talk about how to solve the fin equation if we consider a fin of uniform cross-section. So this is the equation we derived in the previous video to describe the energy balance on this fin. Okay, so theta is our dimensionless temperature, z is our dimensionless length scale. So theta is going from 1 at the base of the fin to 0 would be theta as the cooling fluid. You can go back. This is the kind of conclusions from the last video. We did an energy balance on an arbitrary fin, non-dimensionalized it to get this general fin equation to solve. So let's solve it. And if we rearrange this equation a little bit, I mean, this is a nice, beautiful equation, how something complicated as heat transfer down a fin can be expressed by this really simple equation. That's the beauty of non-dimensionalization and, defining these parameters like m. We get this really coherent, nice expression. D squared theta dz squared equals m squared theta. Okay, so this is telling us that theta must be a function equal to its derivative, or really second derivative. So we need to guess usually a lot of times to solve these problems, what would be a good function that would satisfy this criteria. So I don't know what you'd think. Perhaps e to the x would be a good function because we know that dex dx is equal to e to the x. Okay. So this, we can do it twice. And, this expression, there are other good guesses too, but this is a good one that you can plug in. And of course, this is very common for second order, first order differential equations to guess this. So let's do it. Let's plug it in. Let's guess that theta is going to be equal. I'll put a question mark to e to the mz. That way, the m, when we take the derivative, the m will come out front, hopefully. And so we can test it out. What we want is plug in our guess for theta into this expression for the left and right hand side. So on the left hand side, we've got the second derivative of e mz, which is second derivative of theta with respect to x, is going to be equal to m squared e mz. Okay, so this is the right hand side. So let's do it. Let's take one derivative on this left side, take the derivative of e mz, and you're going to get the m to come out front of the derivative of e mz dx. Okay, has to equal, and we'll put a question mark. We don't know if this is true. Has to equal m squared e mz. Take the next derivative. We're going to get an m squared out front. E to the mz equals m squared e mz. So let's get the green pin out here and let's put a check mark. This is true. So the second derivative, if this is theta, then the second derivative equals m squared times the function itself. So this is what we call a particular solution. Okay, so this is going to be called particular solution number 1. And there's also other good guesses. I mean, these e functions, you can imagine that if we also guessed theta is equal to maybe e to the negative mz, that this would also work out. And in fact, it does. So let's prove that. To make this valid, let's plug this theta into this equation that needs to be solved. So it'd be the second derivative of e to the negative mz dz is equal to m squared e to the negative mz. So take one of the derivatives, you'll get a minus m out front. So you get minus m times the first derivative of e mz dz equals m squared e minus mz. Take the other derivative on the left-hand side, and you'll get another, this is minus. You'll get another minus m to come out front. So there's going to be minuses will cancel out. You'll have m squared m squared times e negative mz equals m squared e negative mz. Boom. Everyone's happy. This is also a solution. So we'll call this particular solution number 2. Okay, so now we have two particular solutions. So when we have two particular solutions, let's look at them. This is our first one, e to the mz is going to come across and go up an exponential function, crossing at z equals 0 at 1. And the negative one, of course, comes down, and these are exponential, so, as it goes to infinity, it'll approach 0. And these are linearly independent, meaning that they're not a multiple of each other. You can't just multiply this by the other one or by something to get that equation. So these are two linearly independent solutions. And the theorem for solving these differential equations is that if you know two linearly independent particular solutions to a linear differential equation, okay, so this is a second order homogeneous linear differential equation, then we know the general solution. And the general solution would be the sum of two linearly independent particular solutions, okay? So that means the general solution for theta is going to equal sum C1 e to the mz plus C2 e to the minus mz, okay? So we have some combination of these particular solutions. And we can also express this in other ways. You did not have to pick e as the function that we guessed. You can also use trig functions. And that's because these trig functions a lot of times are the same as these exponential functions. Okay, they're just different ways to write it. So let's write this. Let's write e in terms of trig functions. And the ones I'm talking about in particular are hyperbolic sine. We'll call it sinh. So this is the hyperbolic sine of x. And this is the definition of that in terms of an exponential function is e to the x minus e to the minus x over 2. And there's also cosh, okay, so hyperbolic cosine of x. The definition of that is e to the x plus e to the minus x over 2. And so you can imagine that let's rearrange this. Let's take some arbitrary constant, let's call it C3 to clearly indicate this is a different constant than, C1 and C2 written here. So if you had some combination of sinh and cosh as your particular solutions. So some sinh of x plus C4 cosh of x. Let's say, is this your solution? Let's rewrite these in terms of the definition of a trig function. So this would be C3 e to the x over 2 minus C3 e to the minus x over 2 plus C4 e to the x over 2 plus C4 e to the minus x over 2. Let's lump these terms e to the x together. So this is going to be C3 plus C4. And then your e to the minus x terms is going to be C4 minus C3. So you have C3 plus C4 over 2 e to the x plus C4 minus C3 over 2 e to the minus x. And this is the same as C1 e to the x plus C2 e to the minus x, okay? So you could plug this in for your general solution or sinh cosh, okay? These are both your solutions, and you can even see how the constants would be related to each other between them, okay? But they're different if you use the different functions, but it doesn't matter because we don't know what they are anyway. They're arbitrary constants. They just happen to be arbitrarily different from each other. So what are sinh and cosh? These are imaginary part of complex trig functions, okay? So for example, sine of the imaginary part of x, of a complex function, sine ix equals I sinh x, okay? Same thing with cosh. Cosine of the imaginary part is equal to cosh x. So this is kind of the definition of hyperbolic sine and cosine. And we can look at some of their properties. This is cosine, hyperbolic cosine. This is hyperbolic sine. And we know cosine of 0 is 1. This is like a common function. So also the cosh, hyperbolic cosine of 0 is 1. Okay, so these are very similar. Sine of 0 is 0. Same thing. We'll say hyperbolic sine of 0 is equal to 0. Cosine, we know, is an even function. So cosine of a negative number is cosine of the positive version of that number. That's the definition of an even function. So cosine of, let's say if this is 2, cosine of 2 equals cosine of minus 2. It's the same. It's an even function. So it's evenly reflected about itself. So the example I just gave is cosh. So cosh also satisfies that. It's an even function. And sine is an odd function, okay? So it's the same thing here. Sine of 2 is going to be some function, and then cosine of -2 is going to be negative of that. So an odd function is where sine ix equals I sine x. So same is also true for sinh of -x equals negative sinh x, okay? So they're very similar, but the hyperbolic functions are not periodic, okay? So they're almost like these exponential functions in the way that they're not a periodically repeating function, but otherwise they have very similar properties. And so the takeaways are we have a fin of uniform cross-sectional area, and we want to solve the differential equation which describes this fin. Of course, here we see what this M parameter is as a collection of constants which describe the properties of the fin: length, convection on the outside, thermal conductivity down the fin, cross-sectional area. And we showed that this is the general solution, okay? There's two ways to write it. So it's either sum of exponentials or sum of hyperbolic sines and cosines. They're the exact same thing. It just some boundary conditions are easier to plug in certain versions of this equation. And so also to keep in mind that theta is a dimensionless temperature and z is a dimensionless length scale down the fin. And so that's it.